So exercise 1, we are going to derive very basic Solow model. Alright? So now we are making assumption. Okay? Making an assumption that we are given Kaplan-Meier production function, and in this economy, fertility rate and mortality rate is same. If fertility rate and mortality rate is same in the long run, it means that population doesn't change. Yes? Doesn't change. Labor will not change. So in other words, we know that change in labor, okay, with respect to time is going to be 0. Right? 0. Or let's write this change as L dot, okay? L dot. Change is 0. Or growth rate, which is change in labor over labor, is going to be also 0. Yes? Growth rate. If the change is 0, growth rate is also 0. Population is not growing. Okay. So Kaplan-Meier production function is given for us, which is output times technology, okay, times capital in the power of alpha times labor in the power of 1 minus alpha. And now we are making an assumption that factor of productivity, which is technology B, is constant, is not going to change. Okay? It is constant. So in other first, number 1, now we have to derive the law of motion of per capita capital. Okay? The law of motion of per capita capital in continuous time. So in order to derive it, first of all, we have to find the per capita value of our output, yes? In order to find, we have to divide both sides of this equation by labor, right? So our per capita output is equal to total output over labor, right? And we know that total output is equal to technology times capital in the power of alpha times labor in the power of 1 minus alpha over labor, right? Or you can write the technology times capital in the power of alpha times labor in the power of 1 times labor in the power of minus alpha over labor, which has 1 exponential power. So if you cancel out these two, you will get technology times capital in the power of alpha over, because it has minus, labor in the power of alpha, or technology times capital over labor in the power of alpha. Capital over labor, it gives us technology times per capita or capital per worker, right? Capital per worker, small k, okay, in the power of alpha. So we will be using it over and over time, okay? So now let me write down. So our output per worker is equal to technology times capital per worker, okay? Capital per worker in the power of alpha, okay? So now, here, when we did it in discrete time, also now you don't have to write what I'm writing now, okay? In discrete time, in order to derive the law of motion of per capita capital, the initial step we considered what our capital for the next year is equal to, right? Then, which is equal to capital stock, don't write it, okay, minus depreciation rate of capital, which is going to depreciate, right? And plus investment. We consider this equation and then step by step derive our law of motion of per capita capital, which we did it during the lecture. Okay, it's in your notes or in the slides. You can easily find. But in continuous time, this equation is not considered. Okay, is not considered. Rather, we are going to consider number 1, what per capita capital is equal to. Per capita capital is equal to capital stock over labor, right? It's number 1. Second, number 2, step. You have to take natural log of this equation from both sides. if you take natural log, then you will get natural log of per capita capital equal natural log of capital stock minus natural log of labor. Okay? So you will get this one. And step 3, you have to take first difference of this equation. First difference. You can take first difference, with respect to change in per capita capital, or you can take first difference with respect to change in capital stock or labor. Right? But if you want to figure out change in all factors in here, you have to take first difference with respect to time. Okay? Over time, they all change. So, first difference, okay, you have to take first difference with respect to time. Time. So now, if you take first difference with respect to time, you know what is it, right? So now, change in per capita capital with respect to time. What is the first difference of L and K? It is
1 over K.
1 over per capita K, yes? Equal change in capital stock or with respect to time times 1 over capital stock, right? Minus change in labor with respect to time times 1 over labor. Okay? 1 over labor. 1 over labor. So this one we already know, right? Oh, let me keep it. Okay. So look, in order not to write these, changes with respect to time, many times, let's give one symbol which is going to represent it, okay? Let's say that change in per capita capital with respect to time gives symbol per capita capital dot. Okay? Change in capital stock with respect to time, say it is K dot. And change in labor with respect to time is L dot. Okay? You just keep it because we will be rewriting it many times. So now if you rewrite it, what you are going to take, so change in per capita capital, right? Over per capita capital is equal change in capital stock over capital stock minus change in labor over labor. So we made strong assumption, right, that fertility rate and mortality rate is same. If it's same, change in labor is going to be 0, which means that this is equal to 0. Yes? It's 0. Now here it is equal to 0. Or you can write it, so change in per capita capital over per capita capital is equal to change in capital stock over capital. Okay? And during the lecture, we discussed what capital for the next year is equal to, right? So which is, capital for the next year is going to be equal to capital, right, of previous year, which is going to depreciate, yes, and any change will caused by investment, right? Investment. So now if I subtract both sides of this equation, KT, capital stock, then I will get KT plus 1, capital stock, minus capital stock of previous year equal
SY.
Investment minus depreciation, right? Which gives us change, right? Or graphically. So this is production function. Yes? This is investment function. depreciation line, right? So we said the capital of KT, right? Of year T. So what about KT plus 1? We said it's going to change. So now this is our investment line. This is our depreciation line, yes? So which means it was capital, this much depreciated in 1 year. But this much was invested. Which means that this much of an investment was spent for compensating that loss. And that capital increased by this difference. Investment minus depreciation. So next year increased by this change, okay? By this change. So which represents this? Investment minus depreciation. So in other words, this is change in capital, okay? Change in capital is investment minus depreciation. So now we will plug this investment minus depreciation instead of this change. So if you plug it here, you will get change in per capita capital over per capita capital is equal investment minus depreciation over capital. So then, if you simplify it further, that change in per capita capital over per capita capital is equal to investment over capital minus depreciation, right? Because these two capitals will be cancelled out. Okay? So now at this step, what should you do? So now here you plug into this one, this equation, right? And now here you have to multiply both sides of this equation by per capita capital, by this denominator. Okay? So then you will get change in per capita capital is equal investment over capital times per capita capital minus depreciation rate times per capita capital, or depreciation of per capita capital. Okay? So in here, what should you do? You know that per capita capital is equal to capital stock over labor. So now you have to plug it in here. So why do we do it? Now we'll see. If you plug that, you will get change in per capita capital is equal to investment over capital times capital over labor minus depreciation over capita capital. So now we can cancel out these two capitals, right? What we have left is change in per capita capital is equal to saving rate times per capita output over labor minus depreciation rate times per capita capital. What does output over labor gives us? It gives us per capita output. Yes? Output per worker. So change in per capita capital is equal to saving rate times per capita output of output per worker minus depreciation rate times per capita capital. So this equation is called the law of motion of per capita capital. Okay? This one. This is called, now we did the first one in continuous time. When you did it, or when we did it in discrete time, how the law of motion looked like? It was like, you don't have to write this one because you have this. So capital, per capita capital in year T plus 1 minus per capita capital in T, it was investment minus depreciation. It was like this. If you compare the previous, the law of motion derived in discrete time and in continuous time, it is same. No difference. But in the second exercise, we are going to derive with population growth, which the law of motion is going to be different. Okay? And that difference is included. Okay, good. We are done with this one, number 2. Find the steady state level of per capita capital. Oh, I erased the graph. Okay, let me draw it once again. So output function, investment function, and depreciation line. So now we are asked to find steady state level. So now if our capital was somewhere here, right? Because investment was greater than depreciation. Next year the change is going to increase capital. And it will continue until this point. Capital will be growing. And if capital grows, output also will be growing, right? So now at this point, investment and depreciation is going to be same. It will be same. After this point, capital will reach steady state level. Which means that after this one, capital is not going to change. Because whatever, invested is just enough for compensate depreciation. Okay? And output after this point is not going to change. Which means that people in the long run will be consuming this much forever if nothing changes. Okay? So now we are asked to find this steady state level of per capita capital. Okay? We already made arguments that investment and saving is going to be same, right? Which means that it is investment, it is depreciation. So now, the difference between these two is going to, change in per capita capital is going to be 0. Okay? This is an important point. So now we find steady state level, okay? Number 2. So it's 0 equal investment minus depreciation times per capita capital. It will be 0 if per capita capital is in steady state level. Okay? So now what our per capita output is equal to? It is equal to technology times per capita capital in the power of alpha, right? We will plug it there, here. 0 equals saving times technology times per capita capital in the power of alpha minus depreciation times capital in the per capita capital. So these are in steady state level. Okay? In steady state level. Saving rate is exogenous given. Technology is exogenous given. Depreciation rate is given. What we have? Only 5 K star. Okay? So now our depreciation rate times K star is equal to saving rate times technology times K star in the power of alpha. If we divide both sides of this equation by factors that we need, we will get K star over K star alpha. Yes, I divided both sides for this one, and depreciation. Saving rate times technology over depreciation. And now it is equal to K star in the power of 1 minus alpha equals saving rate times B over depreciation, or it is equal to our K star, steady state level of per capita capital is equal to saving rate times technology over depreciation in the power of 1 over 1 minus alpha. So this is the steady state level of per capita capital. Okay. This one. Everything is given. So now we found it. Next, find the steady state level of per capita output. Per capita output. We know our per capita output is equal to technology times per capita capital in the power of alpha, right? Our per capita output is going to reach the steady state level if capital is in steady state level. We already know what steady state per capita is in steady state level. We just plug it in this equation and we will find it, okay? Easily. So our per capita out in steady state level is equal to technology times saving times technology over depreciation in the power of 1 over 1 minus alpha in the power of alpha. So if you simplify, take this b out of the brackets and make all the calculations, you will get your per capita output in the steady state level is equal to technology in the power of alpha. So 1 over 1 minus alpha, okay? And times saving rate over depreciation rate in the power of alpha over 1 minus alpha. So now this is steady state level of output per worker. Output per worker. And the last fourth one, find the steady state level of per capita consumption. Per capita consumption. Okay? Per capita consumption. What per capita consumption is equal to, we know consumption is equal to consumption rate times income. If you divide both sides by labor, both sides by labor, you will get consumption per capita is equal to consumption rate times output per capita. Yes? Output per capita. Or this consumption rate is equal to consumption rate per capita consumption is equal to consumption rate is equal to 1 minus saving rate times per capita output. So now we are asked to find steady state level. We start. It will reach the steady state level is our output is in steady state level. We already found what it is equal to. You just plug and you find. Okay? So now our steady state level of per capita consumption is equal to 1 minus saving rate times technology in the power of 1 over 1 minus alpha, saving rate over depreciation in the power of alpha over 1 minus alpha. So this is steady state level of per capita consumption. Okay? This is it. So now we solve first exercise, we derive everything. Okay? So it is in the case of when we consider there is no population growth. Okay? There is no population growth. So now I'm going to erase it and we will do exercise 2. Exercise 2. Okay. Exercise 2. Solow model with population growth. Again, we are considering, exactly the same continuous production function. All right. And we are making assumption that technology is constant, not changing, but what is changing now, population is growing. And growth rate is equal to n. Okay? So where we can write change in labor with respect to time, okay, which is equal to population growth times labor. Right? Or change in labor, let me write it as this one, okay, as we did there, over labor is equal to growth rate of population. Why is it so? If you write it in discrete time, right? Let me quickly write here. So L, when we say change, it is labor T plus 1 minus labor T, right? Which is change, over LT is equal to that growth rate. Or you can write it, let's suppose that our LT plus 1 minus LT is equal to growth rate of labor times labor. Yes, if you take it to this side, you will get labor T plus 1 is equal to N times labor T plus labor T. Or you can write it, labor for the next year is equal to 1 plus N, yes, LT, which is our next, it will grow by this much. So this is, that it tells us that story, okay? So if you need it, you can write it right now. If you don't, there is no need, okay? Good. Number one, now we have to again derive the law of motion of per capita capital when population is growing. When population is growing, as we did previously, that our aggregate output is equal to technology times capital in the power of alpha times labor in the power of 1 minus alpha. We have to turn into per capita terms. If we divide both sides by labor, we will get that our per capita, as we did previously, our per capita output is equal to technology times per capita capital in the power of alpha. We did it in previously, right? It's equal to this one, okay? So, in continuous time, right? Derived in continuous time, what we consider first, what our per capita capital is equal to, right? It is equal to capital stock over labor. Second, what we did, we took natural log from both sides of this equation, right? Natural log of per capita capital is equal to natural log of capital stock minus natural log of labor. Then, after this one, step 3, we took first difference, right, with respect to time. So, change in per capita capital with respect to time times that first difference of L and K is 1 over per capita K is equal to change in capital stock with respect to time times 1 over capital stock minus change in labor with respect to time times 1 over labor. Again, in order not to write it many times, let's give them these symbols, okay, as we did earlier. So now, change in per capita capital over per capita capital is equal change in capital stock over capital stock minus change in labor over labor. So, we discussed that if our population is growing, what change in labor over labor is equal to? Population is growing. It is equal to growth rate of population, right? It is equal to N now. Okay, which is given for us. So now you can write that change in per capita capital over per capita capital is equal change in capital stock over capital stock minus growth rate of population. Okay. So at this point, what did we do? We know that we did change in capital stock is equal to investment minus depreciation. Now we apply it here again. Then we will get that change in per capita capital or per capita capital is equal to investment minus depreciation of capital over capital stock minus growth rate of population. Then at this step, we multiply both sides of the equation by per capita capital, which gives us change in per capita capital is equal to investment minus depreciation of capital over capital times per capita capital. Or just a second, let me simplify it first, then multiply, okay? So, in order to, so now if you write it as saving investment over capital minus depreciation, right? Minus depreciation, minus N, right? And now if you multiply both sides by per capita capital, okay, it was and over K, right? Now we'll multiply. If you multiply, then you will get change in per capita capital is equal to investment over capital times per capita capital minus depreciation plus N times per capita capital. Yes? Okay. After this point, what we did, we plugged the value of what our per capita capital is equal to, right? Capital stock over labor. So once we did it, then you get change in per capita capital is equal to investment over capital stock times capital over labor minus depreciation plus N times per capita capital. We cancel out these two. What we have is per capita output. Per capita output, right? Change in per capita capital is equal to saving rate times per capita output minus depreciation plus growth rate of population times per capita capital. So this is the law of motion of per capita capital when population is growing. Okay? When population is growing. Okay? So, if you refresh your memory about the lecture, when we derived it in discrete time, it was a bit different. Okay? So it was our per capita capital of next year minus per capita capital of this year was equal to 1 over 1 plus growth rate of population in the parentheses that investment minus depreciation plus N times per capita capital. It was like this. Okay? In continuous time, it is not anymore here. So which means that if we are going to apply it to generate data in the computer, because in continuous time it is missing, we are not able to do it. It is only possible in discrete time. Okay? Discrete. I will show you later. So, but if you get the difference between these two, okay, because it's going to be very small change, okay, in here, the result that you get is going to be very close to each other, okay, close to each other, okay. Next, find the steady state level of per capita capital, okay. Before we do that, look, graphically. So it is output function curve. This is investment function curve. And let's suppose it is the curve that, that straight line of depreciation without population growth. Okay? Population growth is not there. So it's this one. But now we are considering, let's suppose, two economies. In one, population is not growing, right? Function, everything is same. But in the second economy, population is growing. If population grows, okay, then this depreciation line is going to be steeper like this. Okay? So which will include that the depreciation plus growth in population K. Which means that if population is not growing, the economy will reach steady state level of K star, and output will be Y star in here, and consumption is going to be this much. While in a country with everything same, the only difference population growing, it will reach much less steady state level of per capita capital. It will reach that level where steady state level of output is going to be less and consumption also less. Okay? We are making argument that after this point consumption is not going to change. So which means that if in these two countries, a country with low population growth, will reach higher consumption in the future, and they will be living better than this country with population growth. Okay? And Solow, for example, this kind of arguments and findings, it is really good to apply for policy making. So therefore, some countries, they are trying to reduce population growth. Why? In the long run, we don't want to have to end up with having less consumption. Okay? So now, if it's the case, we have to find steady state level of per capita consumption when population is growing. Now we'll find it. Okay? So we said that when it reaches investment and depreciation is same, so there is no change in per capita capital. It means that it is equal to 0, yes? Change in capital is equal to 0, equal saving rate times per capita Y minus depreciation plus growth in population times per capita capital in steady state level. We know what our Y is equal to. 0 equal saving rate times technology times per capita capital in the steady state level in the power of alpha minus depreciation plus growth in population times per capita capital star. So once we do all simplifications, you will get delta plus n K star equal saving rate times technology times per capita capital in the power of alpha, star in the power of alpha equal saving rate times technology over depreciation rate plus growth rate in population. So if you do all the simplifications, you will get that per capita capital in the steady state level is equal to saving rate times technology over depreciation rate plus growth rate in population in the power of 1 over 1 minus alpha. Okay? You will get this as we did it earlier. What is different? If you compare with and without population, the only addition of is growth rate of population. Okay? Good. So now we have to find steady state level of per capita output. Okay, per capita output. Again, as we did it, our per capita output is going to reach the steady state level if our per capita capital is in steady state level. Yes? So we plug everything that we have already found. Our Y star is equal to technology times saving rate times technology over delta plus n in the power of 1 over 1 minus alpha in the power of alpha. So our Y is equal to B in the power 1 over 1 minus alpha times saving rate over delta plus n in the power of alpha over 1 minus alpha. So this is in the steady state level. Steady state level of per capita output. Right. And regarding consumption, that we already know, our consumption is going, per capita consumption is going to reach steady state level, 1 minus saving rate times output in the steady state level, or we can write it because it's found already, 1 minus saving rate times technology in the power 1 over 1 minus alpha, saving rate over depreciation plus growth in population in the power of alpha over 1 minus alpha. Okay? So this is steady state level of per capita consumption. Per capita consumption. Okay? Per capita consumption. So regarding consumption, we already found so now we are going to do exercise 3, all right? Then I will give you 5 minutes break. Exercise 3. So now I'm erasing this side. Exercise 3. So now we are considering an island, okay? Where lives only one person. This type of economy we consider as Robinson Crusoe's economy, okay? So island with one person. And we know that Robinson Crusoe's production function is given. If, so which is production function is equal to y equal to technology times capital in the power of 1 over 2. If it's one person economy, there is no difference between total output and per capita output, right? It's same. It is same. Okay. So look, now we have another data. You know what happened to Robinson Crusoe? They had that, you know, that accident, right? He reached that island. The next day when he woke up, he saw that the ship is still there. He swam back and he found a dog and he got, you know, some needed stuff and brought it back, which was capital. Okay? And that capital he brought was equal to 100. Okay? Capital is 100. Okay. So, question number 1. If the country devotes 30%, or Robinson devotes 30% of its output for making investment, good, okay? How much is he saving?
70%.
How much is he saving? Okay. So let's find output. Can you find output with given capital? Capital? Yes, right. Our output is equal to 4 times 100 in the power of 1 over 2, which is equal to 40, right? Investment. How much investment is made? We know that investment is equal to saving. And saving is equal to saving times output, right? So now we know that saving rate is
0.3.
saving rate is 30%, 0.3. So now it's equal 0.3 times output is equal to 40, which is equal to 12. Okay. investment made is 12. Investment made is 12. We found next. Additionally, if 10% of all capital depreciates every year, is the country's output increasing or decreasing? So number 2, which tells us what depreciation rate for Robinson's capital is. It is 10%, right? In other words, capital is going to depreciate by this much. So 0.1 times 100, which is equal to 10. Is it increasing or decreasing output? So if you draw it graphically, so which is production function of Robinson, okay? And this is that investment function of Robinson, and this is going to be depreciation line. So capital is somewhere here, 100. And when it was 100, he was able to produce 40 units of output, yes? And investment at this point was equal to 12. And depreciation is 10. And how our capital is going to change for the next year, it is the difference between investment and depreciation. Which is it positive or negative? Positive, right? So investment is greater than depreciation. Which means that next year, capital is going to be increased by this much. Right? By this much too. So which means that capital is growing. Capital is growing, output also will grow. And it will grow up to this point where Robinson will reach steady state level. So economy is now growing. It's growing. The answer is growing. Next. How much will be the capital stock of the following year? From here we know 102, yes? Or that with the given equation we can simplify that our KT plus 1, which was KT, is going to be equal that capital T of capital of last year, which is unfortunately depreciates, yes, plus investment, which is equal capital we already have, which is equal to 100. Depreciation we found, it is equal to 10. And we already found what investment is, which is 12, and it will give us 102. 102. Okay? 102. So for the next year, it is 102. Okay? Good. So next one, number 4. Find the steady state level of capital stock and output. Here, stock per capita doesn't make difference, right? Per capita, capital, and per capita output. Steady state level. Now we are asked to find this one and this one. Y star and K star. If you look at your notes that you have taken, you already know when population does not grow in the economy, what will be the steady state level equation? We found that steady state level of capital per worker is equal to saving rate times technology over depreciation in the power of 1 over 1 minus alpha. Yes? It was that we derived. And now we have everything found. Saving rate is given, which is 30%. Yes? 30%. 0.3. Technology is given, 4. Right? Depreciation rate is 10%, 0.1. In the power of 1 over 1 minus what is alpha is equal to? 1 over So which is equal to, it will be 3, 12, 12, and it will be squared, 12 squared, it's going to be 144. 144. So which means that Robinson Crusoe's economy will reach steady state level when capital is equal to 144. Okay? Good. Now we should find the per capita output. You know the per capita output steady state level is equal to technology is equal to 4 times, and our per capita capital in the steady state level in the power of 1 over 2, yes?
Yes.
So now it's equal 4 times 144 in the power 1 over 2. It's equal to 4 times 12. It is 48. So output is 48 at this point. And then, and now we already draw it graphically, okay? Graphically. And the last one, how much is Robinson going to consume when it reaches steady state level? How much is going to consume? Okay? C star. So, per capita consumption is equal to 1 minus saving rate times per capita output in the steady state level, right? So, which is 1 minus 0.330% times 48, and it's equal to 33.6. 33.6. Okay? So now we solved it. We solved it. Okay? We solved it. So now we are done with exercise 3. Okay? So now we have exercise 4. Exercise 4 is exactly the same with exercise 3. Okay? Now you can see it. So what I'm asking you to do, you have to do the same steps. Okay? What's the difference is the only capital stock. Production function of Robinson Crusoe is same here. Saving rate is 30%. Depreciation rate is 10%. Okay? So now the only difference is capital, which means that Robinson was able to reach that ship and bring too much capital. Okay? So now please, you already know how to find and calculate, right? Quickly applying the steps that we did, find what Robinson's output is equal to, and investment he's making, depreciation, okay? And next year's capital. You have to find 1, 2, 3. You have to solve it. Regarding 4 and 5, it's going to be same. Because it's same type of economy, steady state level will be same, no difference. Alright? So please quickly solve it. I will ask you what is it equal to. got some solutions. What is Robinson's output when capital stock was equal to 324? 72, right? Output is 72. What about investment he's making? 21.6, okay. What about depreciation? 32.4. And next year's capital? 313.2. Okay, good. So now, this is in the case of when capital is too much, yeah? Now, it was the graphic that we derived. So you can see that steady state level was reached in 144, where capital was 100. Function is same, right? Exogenous factors are all same, but now capital is 324. When it was 324, output reached this level, which is 72, right? And depreciation, let's make it like this. It is 32.4, while investment is 21.6. Next year's capital is now decreasing, right? We know that this horizontal line does not represent time, it represents capital. So which means that next year capital is going to change by this much, right? Why it is decreasing? Because investment is less than depreciation. Investment minus depreciation is now negative. So therefore it will be moving to the left. Yes? So now it will be decreasing over time, and it will reach this steady state level. If you derive it in this case, again, you will get exactly the same values. No difference. Okay? So now, economy's output is declining. Why? Because it's too much. Depreciation is higher than investment. Look, but if you compare, when country has too much capital, of course they will be consuming more, okay? And over time consumption is going to reduce. And it will reach the steady state level. After this point, consumption is not going to change. Okay? It's not going to change. Alright? So now we are done with this one. Exercise 5, which is comparative exercise, okay? Comparative 1. Let me erase the board. So now we are considering two countries, right? Country A and country B. Country A and country B. And we have data given for both countries. First of all, we have given population growth in both countries, which shows that in country A, growth rate is 1%, 0.01. In country B, it is 5%, 0.05. Production function for both countries is same. Output is equal to technology times capital in the power of 1/2 times labor in the power of 1/2. More data is given. Depreciation rate and saving rate for both countries is same, identical, okay? Depreciation rate for both countries is 10%. And saving rate for both countries is 30%, 0.3. Okay? Now we have this data given. Number 1, by considering the law of motion of capital accumulation, find the steady state levels of per capita capital, output, and consumption in both countries. Now it says, first let's derive it. Change in per capita capital, the law of motion, what was it equal to? Investment, right? Saving rate times output per capita minus depreciation plus growth in population times per capita capital. Right? Okay. So now we should find the steady state level. In steady state level, if this change is equal to 0, right? It's going to be 0. And saving rate times what our per capita output is equal to. In order to find it, we have to divide both sides of this equation by L, yes? Which will give us, it is equal to 2 times per capita capital in the power of 1 over 2. Right? Okay? So now it is saving rate times technology, which is 2 times per capita capital in the power of 1 over 2 minus depreciation plus saving rate times per capita capital. Good. So these are all, it's going to be 0 in steady state level of per capita capital. So now, if you simplify it all, you will get delta plus m per capita capital star equal to saving rate times technology times per capita capital star in the power of 1 over 2. If from this equation find what per capita capital in the steady state level is equal to, you will get it is equal to saving rate times technology over depreciation rate plus growth in population in the power of 2 squared. It will be equal to this one. It will be equal to this one. If you want now, if you find output in the steady state level, which is equal to technology, which is given 2, right? Times capital, per capita capital in the steady state level in the power of 1 over 2. We already found it, right? Which is equal to this one. Now it's equal. Steady state level of per capita output is equal to technology times saving rate times 2 over depreciation rate plus n in the power of 2 in the power of 1 over 2, which is equal to 4 times saving rate over depreciation rate plus growth in population, right? It's equal to this one. If you find per capita consumption in steady state level, it is equal to per capita consumption in steady state level 1 minus saving rate times per capita output in steady state level, which we already found, yes, which is equal to 1 minus saving rate times 4 times saving rate over depreciation plus growth in population. Growth in population. So now once we have it found, we can easily find what our, with all exogenous factors given, this country's steady state level is equal to. Now, country A, let's calculate it. We know that this is the function for steady state level of per capita output for both countries, which is saving rate times 2 over delta plus n in the power of 2 equal. What is our saving rate is equal to for country A? It is 30% times 2 over. Depreciation is 10%, 0.1, plus Growth in population is 1%, 0.01 squared. If you calculate it with your calculators, if I'm not mistaken, you will get it. It's equal to 29.75.
Yes.
Right? Okay. If you find the per capita output in the steady state level, which is 2 times per capita capital in the steady state level in the power of 1/2, you can apply this one, or you can apply this one, even easier, okay? So now let's apply what we derived, which is 4 times saving rate over depreciation plus growth in population, 4 times 0.3 over 0.1 depreciation rate, plus 1% growth in population, and it's equal to, if I'm not mistaken, 10.9. You double check, is it right?
Yeah.
Okay. So, and consumption per capita, which is 1 minus saving rate times steady state level of per capita output. So now 1 minus 30% investment times, which you already found our output in steady state, 10 times 9, and it's equal to 7.6. Okay? 7.6. So for country A, we found it. So now let's find it for country B. Again, we apply the same equation where saving rate for this country is 30%, same, both countries, times technology, depreciation rate is same 10%, but what is different? Growth in population, right? Now it is 5% squared, which is equal to 16, right? Okay? If you find for Y star, per capita output, it is going to be, if you apply it, it's equal to 8. And if you find consumption per capita in the steady state level, it's going to be equal to 5.6. Okay. 5.6. So now, data for both countries in steady state level is found. Next, using the comparative analysis method, discuss these differences. Discuss these differences. Is there a difference between these two countries' steady state levels?
Yes.
The difference is very significant, right? Very significant. Okay, let's graphically show it. Look, if we plot it in the graph, both countries' output function is same, because investment rate is same, investment curve is also same, yes? But what is different is their
Growth rate.
growth rate, right? For example, for country A, where depreciation rate plus growth rate of only 1% times per capita capital, yeah? And it reached this steady state level, yes, which was equal to capital 29.75, and at this point output was equal to 10.9, and consumption 7.6, right? Okay. But in the case of country B, now it is different. Why? This slope is now steeper. This slope is now steeper, which is that depreciation rate plus growth of 5% times per capita capital, with it reached steady state level at this point, which is equal to per capita capital is equal to 16, output at this point is 8, and consumption is 5.6. 5.6. Now we know that these countries, both countries, somehow, let's say, they started with, in this point, with the same capital, okay? country B, while growing, it reached capital of 16 and stopped growth. It stopped. People started consuming 5.6, units of consumption forever. While country B, country A, with low population growth, it was still growing, and it reached this steady state level, and they reached a consumption of 7.6. Okay? So what's the conclusion in here? What's the conclusion? In the last question, we asked, if there is significant difference, we see that this difference is very significant, right? What kind of policies or strategies should a country with lower level of consumption apply?
They should include growth.
So like China did.
Yes. Here, because now we are considering population, one way, or country may, consider how to increase investment, right? But investment rate increasing is not liked by people, because to reach the steady state level it will take too long, which I will show you in the computer. Okay, it's going to take too long. So therefore, they try to approach some policies which is designed to reduce growth in population. China did it strictly, one-child policy, for example. It's not only they were basing, there were some other reasons too. It's one reason, okay? In some countries they use propaganda, right? So which part of the world today is suffering, with the problem of poverty the most? Africa, especially sub-Saharan Africa, right? And because of, that strategical goals of, United Nations, right? Sustainable goals. And what's the first sustainable goal? No poverty, right? So now, according to them, by 2030, it should be close to 3%. Unfortunately, so many things has changed. We don't know whether it will reach or not. And because of that importance now, so many NGOs are now in sub-Saharan Africa. So one thing that they are doing, okay, in there, those NGOs, they are coming to people, to the nation, and now they're teaching them how to have less children. Okay? How to prevent having too many children. They're explaining why it's better to have less children, why it's not good in this condition having too many children. Okay? That way they are trying to reduce that growth in population. Okay? If those countries are able to reduce it, let's suppose in this case, from 5 to 1, it will reach this point, it will shift, and it will reach this point in the long run again. Okay? It will be like this in the long run. So, let me, show it in Excel, the exercise 3 and exercise 4, okay, which will give you more thoughts.
But the consumption as a whole stays the same, yeah? If not taking per capita, but like the total consumption amount, it's staying the same for both countries, is it?
This is per capita.
Yeah, but taking into consideration like the whole consumption?
No. As an aggregate, it will grow. Aggregate capital, it will grow, but per capita will not grow. Okay? Because when labor grows, the output will grow. Okay, it will grow, but per capita will not grow. Okay? Per capita will not grow. Okay, now please look at this Excel file. Let me make it bigger so you will be able to see. Okay. Exercise 3 data is given. Capital is 100, okay? 100. Saving rate is given, depreciation rate is given, and growth in population is 0. 1 Robinson himself, right? Okay, let's derive the data, okay? Our capital is equal to 100, right? This one. What about our output? What was our output function? Is given over there. It's equal technology times power, right? Power of capital. Power of capital in the power of 1 over 2, which is equal to 40, right? Consumption, we know it's equal 1 minus saving rate, which is 30%. Is it going to change? Saving rate? No, it's constant, right? You make it constant. Times output, which is equal to 28. Regarding investment, it's equal investment rate, which is constant, times output, right? Equal 12. Depreciation rate equal is given for us, which is 10%, right? Which is again not going to change, constant, times capital. 10. What about the change? It is investment minus depreciation. Investment minus depreciation. In other words, we can write it investment minus depreciation, it's equal to 2. Our next year's capital is going to be equal our capital of previous year will increase by this change, yes? By this change. Okay? If you apply it for these years, and you apply it for all years, with these changes, with given, okay, you will see that now capital is growing, output is growing, consumption is growing, okay, and now investment is growing, and you can see how long it is going to take for Robinson if everything is not changed, if Friday does not join, okay,
Right.
to take that steady state level. So if you look, it was 144, right?
Yeah.
So it will take 280 years if Robinson does not die to reach steady state level. Okay? So it will reach that level. It takes so long. So this is the reason that long run, if people are asked to invest more, people are not willing to contribute that money because who is going to enjoy it? It's not them mainly, but their ancestors or the future generations, okay? And now, in this exercise 4, we consider capital to be 324, right? If you plug the 324, which is everything is formulated in our, so now you can see, now capital is decreasing, yes? Output is decreasing, and it's also decreasing, and it will reach again, decreasing that 144 exactly after 300 years, okay? After 300 years. So, the last one, the last slide, okay, in here, which I'm not going to explain it to you because I already explained it during the lecture, right? What was behind explaining this one? Government and structural policy. We said, if government expenditure, if government consumes more, then investment in the economy will be less. In the long run, it will reach some other steady state level, which is going to be less. Yes? Consumption will be less. But we gave counter argument, if government is going to increase consumption for these purposes, okay, for these arguments, then it's not going to affect negatively in the long run on output and per capita consumption. It may even affect positively and increase output. Because, for example, investment for education, which is government expenditure, right? It may increase human capital in the nation, and they will be producing technology, okay, this technology, which may be increased and it will be growing. Okay? So why I'm saying it in the final exam, you will have definitely essay type questions, and essay type questions will be this kind of questions. Okay? I will ask, why if government is going to reduce, increase its consumption rate, it's not going to affect negatively on long run growth of output. Then you should explain because of these things. Arguments you can take from here. Okay? So students, we are done.